Okay, we are live. So, let me see. Oh, I have to change it up here. There's too many things to change around here. Oh no! Oh no! At least it's not locked anymore. They had it locked. Oh man! There it is. It's been one of those weeks. Whatever can go wrong will go wrong. All right, so laptop. Oh, yep. All right, that should do that. I guess we better get the lights here. Okay, so in 2018, we did an assessment at the TVA combined cycle plant. And that's a picture of it. Magnolia, beautiful Ashland, Mississippi. And so what I thought is I would like to bring a little bit of that into the classroom. And so this is not particularly well developed. So we're going to jump around a little bit. But this handout is one of a number of EPRI reports. I can't print them all, but what I'll do, I will attach a bunch of them. There's like 3 or 4, and they're like 100, 120 pages each. And this is EPRI, Electric Power Research Institute. They are the R&D arm of the electric power industry. So this is like real stuff for real power plant people and all that. And, you know, I mean, some of it maybe is a little bit deeper dive than we need, but, you know, skimming around and hopping a little bit across it gives you some kind of an idea, you know, at what level the real plant people operate, what they're concerned with, what some efficiency improvement opportunities might be. That give you a little bit of a flavor of, you know, a real power plant and, you know, the discussions and the things that the engineers think about and talk about, and, you know, maybe even propose to improve the operation. So I was looking around, and this is, I don't know, this thing's 130 pages. So I grabbed a little bit of it. This was just one of the ideas that we looked into and made a recommendation on. So like I said, we'll get to that in a few minutes. I'll put it up there, and we'll scan through some of the curves and give you some kind of an idea of what it's talking about. But so this is a picture of the 3 units. So each one of those units, there's 1, 2, 3. You got 3 cooling towers. So the Rankine cycle at the low end of the system, the tail end of it, is rejecting heat to the atmosphere. Each one of those towers, there's 5 cells per tower, has a 200 horsepower motor turning the fan. So in anything small at a power plant, you know, well, actually we did find a couple of small blowers that we made recommendations on, but there's not much small at a power plant. Okay, so each one of those units has a gas turbine. So, you know, it's pulling air into the compressor, compressing it, combustor. You know, that's then going through a gas turbine, coming out. We're going through a heat recovery steam generator. They have duct burners, so they can do supplemental firing to get extra megawatts out when they need them. And then we've got the multiple pressure drums we had a little bit of in that video. And that video link I showed you, you really should watch, because it shows umpteen configurations on this thing. So each one of those is 3 independent units. You know, the offices are over here on the side. We, you know, set up in here, had this big conference room. Went down there, spent, went down one time for a meeting, and then we went down and spent 2 days on site with a team of students walking around and trying to come up with ideas to save energy. When it's your first combined cycle plant you've ever visited, that's a little bit of a challenge. But so this was some of the stuff that we identified areas, and then we have different names of, you know, students or myself, or I don't think Dr. Languri goes with us sometime. I don't think Yeah, he was there, Ethan. Yeah, he was there for this. And then Jeff Marchetta, a fellow at University of Memphis that works with us, he came down for one day of this. But anyway, blowdown. So let's just talk through this a little bit. And so when I say blowdown, does anybody know what blowdown is? What is blowdown? Luke, you know what blowdown is.
How you keep so you don't get scaled and things, you gotta blow out certain particulates.
There you go. So on the Rankine cycle side, you know, we're constantly evaporating water into steam. And we constantly have a little bit of makeup water coming in because you lose some steam here or there. You know, you just lose water from the cycle. Well, when that water comes in, it brings minerals and, you know, we just call it general crud. And, you know, they purify it the best they can, but they can't get it all out. And so in the boiler and the boiling away of this steam, that steam goes away and it doesn't take any of those minerals. So they concentrate in the boiler water. And so if you don't throw some of that away, the concentrations will go up too high and you'll just, it's a hard scale, an insulating scale will form on the heat transfer surfaces, you know, where the steam is evaporating. And it, you know, after a while, it insulates. It's like putting an insulating jacket on everything and you can't operate that way. So in order to keep that from happening, you just drain some water out of the system at pressure and temperature and throw it away. Well, so when you take that fairly high pressure water, 1,000 PSI or something, and throw it to atmosphere, some of it flashes. It jumps into steam. It's called flash steam. And these guys, if you look at this picture, let me see, can you see it in this picture? Yeah, you see these little plumes coming up? See this little white clouds coming out of here? That's blowdown flash. And that's, I mean, once that stuff flashes, it leaves the minerals behind, just like boiling it off. That's good steam that you can recover and do something with. So that was one of our first, you know, I mean, when it, you know, you just drive up and you say, ah, what's that? And they go, ah, that's blowdown. We're throwing it away. You could recover that. Oh yeah, we never thought about that. Because, you know, I mean, they didn't design it. They just operate it. So, you know, that's why you have, you know, people come in with an eye for efficiency. They see things that you might walk by every day and not think about. So that was one of the recommendations. Let's try to capture that blowdown heat recovery in this case. You can also try to collect from the liquid that's left, but that's usually pretty expensive. So I think we wound up just going with a flash on this one. That's kind of interesting. Well pumps. Let me see, can I find a figure on that? So these guys, where these guys got their makeup water, they weren't on a river or a lake or anything, okay? So they would drill wells. And they had daggum wells drilled. They had, I don't know, 20, 25 wells drilled, you know, all over Hell's Half Acre. And then each one, they put a vertical turbine pump and they stick it down. So the vertical turbine pump has a long shaft and the impellers are way down in the water and the shaft comes up and the motor sits up here on top of it. Let me see if I bet I can find some pictures of this. And then you pump it up. Well, I think I've got a, let's see, oh yeah, let's look at screen captures. I got all, here we go. I bet you, let's go extra large. Oh yeah, this is a good way to do this. Where's we got a picture of a control screen someplace. Anyway, I don't think I'm going to find, maybe. You what?
I saw a well pump.
Where, down here?
Right there.
Oh yeah, good. This is one of them. Okay, and so, you know, they got like 15, 18 of these things, and each one can pump, you know, it's got a rating, I don't know, 400 or 500 GPM, and they all pump back to the plant, and they got a big tank, and they pump it in the tank, and then they hold it there, and that's their makeup water for the plant. Well, so if you look at the operation, they had some data on the operation of all of these, and they needed to operate someplace between probably 8 to 9, 7 to 9 of these at a time. Well, some of them would require, I don't know, an extra 50% horsepower, whatever the rating was. You know, these were, I don't know, 50, 100 horse motors, something like that. Maybe 40, 50 horse. I can't remember exactly the numbers. And so we said, well, gosh, why don't you operate the ones, because the ones that are closer, or the wells are not so deep, don't require as much energy to get the water back to the plant. And so, you know, I mean, a well is just a well. Who cares which one we pull it out of? So why don't you prioritize the operation of the pumps based on which ones use less power? And they had never thought about that. They just had the operator. There's the picture someplace buried in there of a computer screen, and it shows all of the different pumps. And the operator just says, okay, I'm going to run this one, this one, this one, and this one. And he's got a flow meter, and he's got a level indicator in the tank. And if the tank level's going down, he turns on another pump and he goes, maybe one more. And he clicks that. And then if it goes up too high towards it gets full, then they start turning them off. And so they just basically control based on this level. And it's a big tank, you know, so it can move up and down and all that's well. So our idea was, hey, let's prioritize the operation of the pumps to minimize the energy. And I went, wow, we never thought about that. You know, it wasn't huge. I don't know, someplace for $30,000, $50,000 a year, which for a power plant is not a lot of money, okay? But anyway, so that was another one of the ideas that we came up with. Let's see. Well, we just do it right here. Cooling tower fans. Okay. So each one of those towers has 5 fans, okay? And in the old days, the old way of operating a cooling tower with 5 cells is to operate, let's say it's cool outside and we don't need full capacity, we'll operate these 3 cells and turn these 2 fans off. And so you've got 2, 4, you're running 600 horsepower. And you've got 400 horsepower off, and you're at 60% capacity. The more energy efficient way is to put a variable frequency drive on each one of these things that allow speed control and operate all 5 motors at 60%. And you say, well, how does that save energy? Well, the cooling tower fan will follow the fan affinity laws pretty well, okay? And the fan affinity laws say that what? Well, for a cooling tower, fan flow is equal to capacity. So if I need 60% capacity, I need 60% fan flow. Okay? So way 1, 3 times 200 horsepower equals 600 horsepower. With the affinity laws, that says so this says if I need 60% of this, I need 60% of this, and speed, fan speed and capacity are 1 to 1, okay? So if I take 0.6 and cube it, because power, the affinity law says power drops with the cube, okay? So 0.6 cubed, 0.6 y is equal to 0.2, it's 216. And I'm going to operate 5 of those, and each one is 200 horsepower. Okay, so what's that's 216, right? Because 200 times 5 is 1,000 times 0.216. Even I can do that in my head. So that's 216 horsepower. And I get my 60% capacity. So would you rather pay for 600 horsepower, or would you rather pay for 216 horsepower? That's pretty obvious. So the recommendation is let's go to variable frequency drives. Now, the rub is that these things, well, you know, they're probably going to cost $150 a horsepower to install. TVA, if you're buying that many, you ought to get a good price, but, you know, I don't know. So 150 times 1,000. So that's 150,000 per unit times 3 units. That's a cool $450,000. Boom. But hey, man, everything's big in the power industry. And so it depends, it depends on the load on the tower, you know, for the entire year, because in the summertime when it's hot and humid, you probably have to run them all at full. But at night it cools off a little bit, and so you can modulate or, you know, you can modulate them down a little bit up and down. And so it's that savings integrated over the whole year that'll determine what the payback is. So anyway, that's what that's talking about. Mist eliminator blowers. Oh man, these were internal to that gas turbine cycle. I can't remember exactly. I can show you, I think we've got pictures. I've got the report here as well. We can thumb through. So these were the recommendations. This is what really got written up and submitted. But if I think I've got some pictures down here. That's just the plant picture. Go down. That's the blowdown calculation. And see, the recovered flash steam was going to go through turbines, so that would get us a little bit of additional power. So that's the on the blowdown. That's the extra kW on the 3 units. So, you know, 97, 87, and 75 kW extra. That's kilowatt hours projected per year. So about 1.77 million kilowatt hours. I think we were using 5 cents, something like that. And then this is an estimation of cost on the blowdown. And so payback, our payback was, you know, 15.6 months. Now, you know, we're not so good at cost, so sometimes this is a trim and impeller. We'll come back to this. I was going to look for this blowers. There's the cooling tower discussion. So there's our CFM, speed ratio equals flow ratio, and then there's the affinity law. So we got some data on number of hours they operated, certain number of fans, went through all that. So projected savings, $90,000, $450,000 investment, a 5-year payback or so. Where was that? 80 months. I don't know. Would you invest $450,000? That's a whole lot better than bank interest, but it's not just wonderful. But I think they did this. They wanted to do this anyway. And so I think they've implemented that. What's the life of what? Oh, a plant like that? Design-wise, probably at least 20 years. But it's like these coal plants, this Kingston we're going to go to. I mean, it was opened in like 1954, and its design life was probably 40 years. So they keep it there. You know, there's a topic in the power industry called life extension. And so that means that you extend the life of a plant beyond its rated life. And you have to do a lot of different stuff. You know, there may be the piping is shot, and you have to rip out all of the main steam piping and put in new. Well, it's cheaper than building a new plant. It's still a big expenditure, but I would say probably 20 to 30 years on a combined cycle plant. There's some cool stuff here we're going to talk about. Where's these blowers? I know we got. Oh, that's good. I'm glad that picture's in there. Duct burner. There's the pump. Come on, Billy. There, okay. Well, let's see, do we have a picture? We have a picture of the blower. They had these little blowers. And see, this is a throttling valve. That's a butterfly valve, and it's throttling. So they were adjusting the flow with throttling, and that's a very inefficient way to do it. So I think if this handle moves all the way down to here, that's closed. And if it moved all the way up to here, one way it's closed, one way it's open. It was approximately damp to, it says damp 40%. So it's 60% open, shown in that figure. Okay. And so you can put a VFD on that and open that thing up and get the same flow at reduced cost. So, you know, they were small, but anyway, that's what that is referring to. Okay, Mr. Lemonade. We were thinking about on the big feed water pumps. Those things are probably 2,000 horsepower, something like that. And if you look at where the feed water actually enters, they just have a throttling valve, a control valve, you know, and it opens and shuts. And again, it's not very efficient, but it was just too expensive. They're also medium voltage. Those things were probably 4,000 volts. And as you go up in voltage, these drives get much more expensive. So that did not make the cut. These were ideas that were generated, and then some of it actually got written up, and some of it didn't. Evaporative cooler pumps. Okay, yeah, we need to let's look. We need to look at this a little bit. This is kind of fun. I gotta be careful. See all photos. Uh-oh. I don't want photos. There we go. There we go. Yeah. Perfect. Okay. So this is where the air enters that is going to go into the gas turbine. And inside this thing, there are filters and there are evaporative cooling media. And so the air gets filtered and it goes through that media, and there's pumps over here, not very big, like 20 horsepower pumps or something, that pumps water up, like distilled water, because you want to keep all this stuff as clean as possible. And it wets this media, and when the air flows through that, it evaporates. It's an evaporative cooler. Okay, so you're in the summertime, this, that, and the other, you can cool down that air. If you cool down that air, it's denser, and you put more molecules into your gas turbine cycle, and you get more power out. So this picks up on this this document here, and so let's look at this a little bit. This is kind of interesting. So now you have this. This is figure 1.1, I believe, and what I handed out to you. This shows just what the addition of the combined cycle. A simple cycle would be just a gas turbine cycle. What page is that on? That's on page 1.2. And so you see, I mean, based on on the megawatts, you see the efficiency increase. So at say 200 megawatts, this simple cycle is maybe what, 37.5% efficient. A combined cycle is about 54% efficient. So that's why you buy that heat recovery steam generator, the steam turbine, put the whole steam, the Rankine cycle, and team it up together. And of course, then you can get larger and larger capacities. So those TVA units were out here about 300 megawatts. And so they were probably 57, 58% rated efficiency. And there's all kinds of stuff in here. So here's combined cycle performance based on locations. So this is kind of interesting. So what's going to be so different between Las Vegas and Miami? Maybe the humidity? Yeah. And so one of the big impacts is when you don't have humidity, the evaporative coolers work a whole lot better because you can evaporate more and you get more temperature depression into your gas turbine cycle, and that ups your efficiency and your power out. So you can see efficiency a little bit better. Net power, oh, it's more in Miami. Well, I'm not sure why that is. Huh. Maybe I should read the report. But anyway, that's what they're reporting here. Site temperature. I'm not sure if this is average or I guess this is at this temperature. Interesting. These are the technologies that were investigated in this report. So, and like I said, I just printed a part of it for you. Evaporative cooling, a media type, that's where you actually have this solid media that the air flows through. Fogging is like nozzles that just spray it. It's got like a spray tree and the nozzles just blow it out. Operating limits, wet bulb temperature on those. Chilling, thermal energy storage, you can actually use chillers and make 40, 42 degree water and use it to cool this stuff down. You get more performance. You have to be careful about having ice because as that air flows through the compressor, it tends to get cold. As it comes through that first stage of nozzles, because you drop pressure on it, it'll get cold and it can cause ice formation and freeze up. We can do in the compressor, interstage cooling. So you know what that's about. We talked about that the other day. And they do have some of these techniques where they actually will inject steam into the compressor to increase the mass flow through it to get a boost in power. So lots of stuff here that's talked about. Let's see. Let's look at some of this. So this was the stuff we looked at because of the evaporative cooling with the rigid type cooling media. So let's see, combined cycle. So, okay, this is simple cycle. So estimated incremental performance of evaporative cooling. So for just the gas turbine itself, 21% enhancement in Las Vegas, 6% in Miami. And that's because it's so dry in Vegas. Heat rate is, we need to define that. We've not defined heat rate in here. That's something that we'll have to talk about. Is equal to the BTUs input per, see, that's an amount, kWh out. Okay? And so if you do it for one kilowatt hour, it's a number usually between 7,500 and maybe 12,000. So like at Kingston, you probably have to put in 11,000 BTUs worth of cold energy into the boiler to get 1 kilowatt hour out. Okay, and so it has units. It's BTUs per kilowatt hour. Okay, now you can do efficiency. A kilowatt hour is 3413, and so you can take 12,000 divided by 3413, and that's 1 over efficiency. And then you have to invert it, because efficiency is what? Output over input. This one is input divided by output. Why they do it that way, I have no idea. But that's just, in the power industry, that's what heat rate is. And so, you'll hear, we go to Kingston, they'll probably talk about heat rate. Okay, so you see there's an impact on heat rate of both the simple cycle and the combined cycle. Okay, so I guess we got some curves down here someplace. This is talking about fogging, where you just spray the droplets. Here's a nice picture. Okay. Plan view, two-sided filter and duct with fogging system. So what do we have? So we've got air inlets, and it goes through the filters. And then we have these fogging nozzle manifolds where, you know, and they want these droplets really fine. If the droplet's too big, it may still be liquid when it gets into the compressor, and it'll slug the compressor. So you got to have really fine droplets, and they want distilled water to make sure that you have clean water. So you got a fogging pump, skid control panel, silencers, whoops, get out of there. Trash screen, duct drain just in case, and then air outlet to gas turbine. Something like that, so it turns and goes out. So that's kind of what a real system might look like. Swirl tube, different types of tubes have been developed in order to, you know, put this water out into the airflow, fine droplets, good distribution pattern so that it will be evaporated. Droplet size, so you see percent at small droplets. So this swirl flash would be much more, this red one would be much better because, see, we get almost all of the droplets down below 5 microns, like 4 microns. Something like that, whereas this guy's got big droplets that could cause a problem for you. Where's some of those? Is this the document you have? Oh, okay, I pulled up the wrong one. I'm sorry. Where is it? This is the one you've got. I'm sorry. I was pulling, yeah, this is the one you've got. Okay. I'm sorry. Somebody should yell at me. All right. Okay, this is on 2.1. You got this one, right? All right. Sorry. But you will have all of them, I promise. So this shows, so it picks a 60-degree ambient as the 100%, kind of like the point of comparison. And so you see, if we decrease, if you just add ambient temperature decrease from this point of 100%, look what happens to the power. I mean, if you put 0-degree air, you get an extra 20% power out of this guy. And airflow, this would be a mass flow because the CFM would be constant, but that's just the density increase of the air. You see, it's going up about 12%, and the heat rate is going down maybe about 3%. So see, cold is good for a gas turbine. And then, of course, you get over here in Vegas, if you're not doing any sort of cooling, so you put, it's 120 degrees outside, what, where's your power? Your power is down here at about 78, 77% of rated. Okay, so that's what this evaporative media is trying to do. It's trying to, in the summertime, when you lose capacity, let you do some evaporative cooling so you can boost the power output, help your performance. Okay. Let's see, where is this? I'm not sure what location. Okay, so figure 2.2 is Kansas City. During testing in August of 97, typical data, what can be expected during the course of a day. On this day, cooling potential. Okay, cooling potential. This is called what? Approach to, there's another term they use. But see, the wet bulb is the limit. If you can saturate the air completely going through the evaporative device, you can get to the wet bulb temperature. You can't get below the wet bulb because when you get to the wet bulb, you're saturated, you can't evaporate anymore, okay? So the dry bulb outside minus the wet bulb outside is the maximum, that's the potential wet bulb depression. So how much can you depress the dry bulb by evaporating to the wet bulb? So that's what this is. So they're saying it was about 8 degrees at 10 a.m., increased to nearly 24 degrees at 3 p.m., and then decreased to 16 degrees by 7 p.m. So, you know, that's the best you could do. And so for this media that TVA was using, they were using a Munter's product called Cell Deck. And Cell Deck advertised 88% efficient, which means you could achieve 88% of the wet bulb depression. So let's say the air was 90 degrees and the difference between those was, let's say it's 10 degrees, then you could get 8.8 degrees taken away from the 90. And so you could be at what, 81.2 degrees. And then you got to look at the performance of your gas turbine, say for that hour, if you have hourly data, see how much enhanced power you're going to get out. And you can also look at what happens to the heat rate, because that's going to tell you how much additional fuel that you may have to put in. Okay, so that's kind of the way this game gets played. And so you can see we've got a plot of the ambient temperature. See if we can get all these. This is the amount of the cooling. This is the wet bulb. And this is the percent relative humidity in the air. And so let's see, cooling potential, temperature, or relative humidity. So I think the cooling is over here on this axis, and the temperature, relative humidity percent temperature. So you can see in through here, I mean, we're getting, you know, we approach 24 degrees, 23, between 20 and 24 degrees for, what is that, 14, 15, 16, so for about 3 hours. So that's what evaporative cooling is all about for you. Here's another one. What is this one? This may be a different example. Assume this. So this is a GE gas turbine unit, combustion turbine, outfitted with inlet display cooler, designed to completely saturate inlet air. Assume also that turbine is subjected to ambient conditions. So anyway, they've got all kinds of plots of this. But if you go all the way to saturation, you do risk droplet carryover into the first stage of the compressor, which could be of danger. And then they talk about humidity. Humidity has a slight detrimental effect. Anyway, I think that's enough of that. Okay. Okay. Huff and puff filters. All right, so this was pretty interesting. This got to be a big bone of contention. So those inlet filters, you know, you saw on that diagram, the air comes in, it goes right to the filter. Well, the filters were designed with a cleaning system called a huff and puff cleaning system. And so it would take compressed air out of one of the stages of the compressor, and ever so often that had nozzles in there, it would blow back at, I don't know, say 50, 100 PSI to clean those inlet filters. And it was set up so that there's an avenue so that that crud can get out of there and not just be re-entrained on the filter. I say, well, that seems like a really good idea. TVA didn't use them. So we, you know, I don't know how we got onto this. We didn't know a lot about huff and puff filters when we got up there. But they are, that pulsing of that filter is controlled by what they call pulse valves. And a pulse valve just fires They probably had a 2 to 3 inch compressed air line going to a manifold, and those valves would fire, pss, 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 or go into a cleaning cycle. And it would pulse, and it would knock the crap off of the inlet filters, which would keep down the pressure drop, which then helps the efficiency of the gas turbine. Well, after a short period of time after operation, these diaphragm valves, these pulse valves have diaphragms in them, and those diaphragms tend to rip. And so when the diaphragms rip, they just leak compressed air like crazy. And so you got a 3 inch pipe or something feeding compressed air to a diaphragm valve that's just blowing air. And that's taken more away from the compressor, because that's coming out of your compressor that's going to your gas turbine. So that's killing you, okay? So TVA just decides, we're just gonna scrap this. So they weren't cleaning them. So they would go like once a year, they would come down, and then they would go in and manually clean these filters. Well, so there is another type of pulse valve that's called a MAC. It's a spool type valve, and it doesn't have a diaphragm in there, so it won't experience those types of failures. So we got all excited. We called the MAC people, and we went down there, and they had conference calls and all this, and it looked to us like a pretty darn good idea. It was going to cost like $1.5 million to replace all of the MAC pulse valves, but if you're going to get an increase in output for the majority of the year, seemed like to us to be a pretty good idea, but TVA wasn't buying it. They wouldn't go down that path. So anyway, that's what the install MAC pulse valves was all about. Let's see. Some of this other stuff, I think that it gets a little redundant. Let's go and let's just scan through the report here for a minute. Let's go back up. That's the flash tanks. We talked about that. But okay, so you know, when you're doing this kind of thing, there's different tools out there. This is a screen capture from a turbine performance model that DOE has out there on the website. So you guys have access to this if you ever need to simulate a turbine. And so you put in these few properties over here. This is the low pressure turbine. So it's going to see 50 PSIG. And basically we're saying it's saturated. Here's the mass flow that we're going to pick up. That's in 1,000 pounds. So that's 1,500, say 85 pounds mass an hour. You have to dig out the isentropic efficiency, and then the generator efficiency it's going to convert to electricity. This was the condenser pressure. So you see we're at a vacuum, which is typical. And then you enter, and it gives you the performance out of this thing. So this thing says this turbine, and so this is just the increase in mass flow based on recovery of the blowdown flash steam. So we're going to put this much more steam through the big turbine. So we didn't do the whole, we just did the increase to see what power that would get. And so that's 97 megawatts, 97.3 megawatts. Oh shoot, that's worth having. So that's for number one. Unit number two came out 87.1, and unit number three came out 75.3. And then you estimate how many hours per year this is going to happen, and put all this together in a nice report. But that's the fundamental engineering behind the recommendation. Okay, trim impellers. So this is this is their closed cooling water pump, and they had one of these per unit. What's the horsepower? And I forget now. 250 horsepower motor, and now they work 4,000 volts. So I think I don't know, did we do a VFD? VFD's impeller trim. Say if you don't want to adjust it, I don't know if we have a valve picture, there's a valve around here someplace that's, this is the discharge line. The suction comes in the middle and then the discharge comes up, and it's a cooling pump. I think that's going to the condensers. I don't have a picture of the valve, but the valve was pretty heavily pinched. Background, let me see. The valve was pinched. I don't know if we put a, yeah, okay. Oh, I know. I remember now. So they had pressure gauges on either side of the valve. And what they did, this pump was too big. It caused problems if they didn't close this valve on it. So they would close the valve until they measured a 20 PSI drop across the valve. Okay, so 20 at 6,500 GPM. So roughly, you can calculate that. The horsepower loss would be 20 PSI times 2.31 converts to feet of head times 6,500 times specific gravity, but that's going to be 1.0 for this. 3960, bunch of constants, divided by the pump efficiency, probably about 0.7, by the motor efficiency, say 0.93, something like that. Right there, that's roughly, that's a pretty decent calculation if that 20 PSI is good. So of that 250 horsepower, 20 times 2.31, so that's 46.2 feet times 6,500 GPM divided by 3960 by 0.7 divided by 0.93. So that's 116.5 horsepower lost across that valve. And times 0.746, we'll give that in kW. So that's about 87 kW. And we've got 3 pumps. So there's a good chance you could do that with an impeller trim. Take the pump apart, take the impeller, take the machine shop, get the pump people to tell you how much to machine off, polish it back up again, put it in, open the valve, and you get the same flow, and you would save that loss across the valve. So if that's times 3, say it's 7,000 hours a year, and we said about 5 cents, something like that. So that's about $91,000 a year worth of electricity, to probably cost you way less than 10 if you can machine them. Yeah. It's the same old story. If you put it in, it's too big, they close the valve. If they put it in, it's too small, somebody has to buy a new pump. If you were designing it, would it be a little bit too big? Probably so. If I was designing it, it would probably be a little bit too big. There's too much risk. I mean, that could be a, I don't know, $200,000 pump. You want to be faced with taking that loose, shipping it back, where you pay a 20 or 30% restocking fee and shipping a larger pump in that's going to cost more money, and the labor and the downtime to put all that together. The world is oversized. Today, that would probably be purchased with a VFD. I'd say if you have a VFD, you don't have to use the valve. Okay, go ahead and oversize it a little bit, but then put your flow meter on it, figure out what you need, adjust the speed, lock it down, you're good to go, or put an automatic control on it. You know, this valve control is a thing of the past, but the whole world in the last umpteen years has been built that way. And so you go to work for somebody, they're not going to have all brand new equipment. I mean, you're going to walk in something, you're going to, oh my God, that thing's like 3 times older than I am. you know, and they expect you to work on it. Yeah, Casey?
I was going to ask you about the configuration of that pump setup. So does that mean that that line coming in, it has, because I noticed most of the time in the other pipes that we talk about, you know, head coming down, supplying the pump. Does that mean that the fluid coming in is like already fresh, you know, it already has energy?
Okay.
So like,
Maybe not. Okay, that's a great question. Okay, so you know, sometimes you have a pump sitting up here, and you just take the pipe and you stick it down in the water, and it sucks it up, right? What's the maximum elevation, theoretically, that you could suck water up into a pipe? This is a great FE question. This is one of my favorite questions of all time. I haven't thought about this in a while. So, okay, so think about it. Let's say that we've got a pipe. So we got that pipe, and it's sitting down here. Okay. And so I got water in here. And it's going to this pump. And this is whatever. That's a valve. I shouldn't put the X in there. Okay. And it's going out someplace. Okay. So to get the water from here, from down here, up through here, up there, what causes it to flow? What does the pump do that allows this water to be sucked up into the back of it?
the water tries to sink up to the level of the water, so water from the bottom flows up and it fills up to the level of the water.
Well, yeah, that's true. And so,
you get started.
well, yeah, but so I mean, you've got this head pushing down to here, but let's say from here to here, so I say to the center line of the pump, what's the maximum height, H max, from the surface of the water to the center line of the pump? How does the pump get it from here up to here? Well, you do it with a straw. Think about a straw. Okay, say you're on top of a 5-story building, and there's you're at Anheuser-Busch. Let's make this fun. And they got a big vat down there that's ice cold. Well, not Anheuser-Busch, what's your favorite? Yeehaw. I love Yeehaw, Dunkel. You know, and I'm at Yeehaw plant, and I'm 50 feet in the air, and they give me this big straw, and it's 1/2 inch, baby. And it goes all the way down there. What do? I start sucking. Okay? So what's the if you had the maximum suction possible capacity, what's the lowest pressure you could get to, theoretically? Absolute zero. Okay, so you got absolute zero here. So what's the other pressure that's helping you? You got atmospheric, right? Atmospheric is pushing down here, right? Well, so let's say atmospheric is 14.7. Well, let's just say 15, whatever, it's easy. PSIA, okay? So if I suck so hard it's zero, what's the maximum elevation that I can be at and get any beer up to me? This is an important question because I like Yeehaw Dunkel. Well, you just convert 15 into feet of head. There you go. If it's water, it's times 15 times what, 2.31. Yeah, 34.65. Well, crap, if I'm on the 4th floor, I might as well quit sucking. Because if I pull that pressure down to zero, that beer is going to get what? a floor below me, and that's a, you know. Now, if I went, you know, if I went someplace and if I could apply more pressure down here, it would push it up further. I might have a chance. So I would say, hey, hold on a second to get my calculator. Can I do this on the first floor? Because I'm going to feel real good after a little while on the first floor. But on the fourth floor, I'm just going to turn blue and pass out with no refreshment, whatever. Okay? So that's interesting.
So I guess I kind of always thought, so that pump it can draw that water up without having any kind of pressure.
That's right.
applied to it at all?
Now, it has to be primed.
Okay.
Yeah, you got to prime it.
Okay.
Yeah, you got to get it full of water. Say, I've got a little swimming pool at home, and if the water level in my pool goes down too much, then and I take the pump, it's got a little top on, it's got a filter in there, and I got to take that, and I lose prime when I do that, and I empty all the leaves and crap out of that, put it back in, man, I got to take a hose, and I got to start trying to dump water in the thing to get enough water in it so that it'll start sucking back. Now, if the water level's high in the pool, it just starts. So there's a difference. If there's a difference of maybe, I don't know, 6-8 inches there that makes the difference between that pump being self-priming and not self-priming. So you do have to get water in it for sure.
Does that mean there's water in the whole line too already?
Yeah. And if nothing leaks, then, but you can buy self-priming pumps that, have a water supply to them that will take care of that. I'm not 100% sure how they do it.
That's what bothered me about that.
Yeah. Oh, no, if that's, but I mean, typically what happens is that, this is probably going to run most of it, but these units do come up and down too. And so there's times, but yeah, they would have to make sure that they keep prime on the pump or it won't.
So like on initial startup, they have to prime that.
Yeah.
Like if they just turn it on, turn it back on, it should be prime.
Yeah. I mean, unless, if there's a leak and that water can leak back down that pipe, back out of it. But so long as that everything is tight and there's no pressure leaks or anything, letting the pressure off of it, it'll hold it up in it. That's just like, like if I get my beer flowing and I gotta go to the bathroom. So if I put a perfect clamp on the top of it, it'll stay right there, right? And I come back and then I just continue. But if my clamp leaks, then that water's gonna leak down and then I gotta work on getting it back up there. That's exactly right. Yeah, these are great analogies. All right, we're about done here. I don't know how good this shows, pump curves, and this is where it was designed. That's 7,000 is designed, and see they had pushed it back to 6,500. So I don't know. Doing the analysis. See what else we got here. Cooling tower fan. We talked about that. I think we talked about most of this. Evaporative cooling. Yeah, there's some of our pictures. I guess that's what we had on the TVA pump skid and all that. Okay, I think that's pretty good. I'm trying to, I've not done this in the past on this because I had not had that experience with the combined cycle. So I'm trying to bring in, more material related to things that I think are more relevant. This course has probably spent too much time in the past just on coal information, even though we're going to go through coal boiler next and just kind of look at all the different sections. So we'll start off on that next time. So, okay, enjoyed it. Have a good rest of the day.
Can you send me that assessment? Because it has the 2 cooling fans on there. And since me and Tyler are working on cooling fans